So this is the second part of the first tutorial, looking at plotting the valence Wannier functions of silicon. Okay, right, so previously we'd run the SCF calculation and also a band structure. So if I list my files, I've got various output files here. So we've still got the results of doing the SCF calculation, but what we would like to do now is obviously generate the Wannier functions. So what we need to do is a non-self-consistent calculation. So that means keeping the Hamiltonian and hence the charge density fixed and calculating it now at a series of k points, not along a high symmetry path as we did for the band structure, but using a uniform Monkhurst pack grid, so just a uniform grid in the reciprocal unit cell. Okay. So what we will need to do then is do that non-self-consistent calculation. So I'm going to copy over o2bands.in into a file I'm going to call o5nscf.in. I'll edit that. The calculation type is now going to be NSCF, for non-self-consistent. I don't want 12 bands. I'm just going to look at the valence bands. So there are only 4 valence bands. So I can put that to 4. That's all fine. Now I don't need this here. So I don't need my k-point path. So I'm going to get rid of those lines. But I'm going to have to put something in its place. So we need to generate a grid of k-points. Okay. So to do that, there's a handy tool called kmesh. Here's kmesh, just to save me typing it in. So if you just run kmesh, it's not on the path, so I have to give this complete path to it. That tells you how we use kmesh. It's quite straightforward. So if I do it 444, for example, that should generate me a k-point mesh, and that's all the information. So that's the coordinates of the k-points and their weight, which is what QE needs. Now, why am I doing this? Kmesh knows about the right precision. Okay, so obviously a quarter 4x4x4 grid is straightforward in terms of precision, but if it was something like a third, 3x3 grid or a 6x6 grid, you need to be able to give it to sufficiently accurate precision, and Kmesh does that for you. So let's pop this in a file. Let's pop it in. Let's call it PW kpoint.dat. Okay, and I can just insert this into my file, and you'll know how to do that with your favorite editor. I'm going to do this with VI, so I need to Control R. There we go. Read that file in, and hopefully that's popped all my k points in for me. Yep, there we go. Okay, I think that is all the things I need to do, so I can now run this non-self-consistent calculation, which might just take a few moments. I will probably edit the video if it does, just to cut out that. Let's call this nscf.out. Actually, that ran really quite quickly. Hasn't generated any errors for me. There's the nscf.out file. I can just have a quick look at that. As a 64 k points, it writes less than 100. It writes them all out. Well, it only took 4 seconds, so that was fine. Okay, so now I need to make the input file for Wannier90, and we've got an example here. So we've got Ex1.win. So I need to tell it how many bands are in my calculation. That was 4. Okay, that's because how many bands I asked in NSCF part. And I also want 4 Wannier functions. Okay, so this is relatively straightforward. This is all good. I'm going to not plot the Wannier functions at the moment. Let's not do that. Let's just get the Wannier functions themselves. What else have we got in here? This is to plot the band structure. This is the path to use. You'll note that's the same path that we used for QE, so we can compare the full calculation. And here I've got the projections. So what the valence bands of silicon, I'm going to imagine that the good guess of the Wannier functions is an s orbital situated on the bond centers, and that's a little bit involved, but that's how to to find the locations of the bond centers. Okay, that's my atom coordinates taken from QE. That's my unit cell taken from QE, and I'm going to have to put in something here. So I'm going to have to put in the MP grid that I'm using. 4, 4, 4, and then perhaps slightly tediously, I do need to describe all the K points. So there is a tool for that. It's the same K mesh that we had before. Where's it gone? There we go. So that's very similar format. I just need to put the word WAN at the end, I think. And if I look at this, there we go. That's all the K points in the same order that QE had them, but minus that last column. So now I can go back to my input file. And pop them all in. So in order to construct the Wannier functions, as we discussed earlier, I'm going to need the M matrix and the A matrix, so the overlap matrix and the projection matrix. So we need to be able to tell the plane wave code what it is that we need to compute. So to do that, we first run Wannier90 in what we would call pre-processing mode. Okay. So to do that, we do Wannier90.x minus pp and the name of the input file Ex1. And that runs in a second, and it's produced ex1.wout, the wout file. That's the output file of Wannier90, and really that tells me about all the inputs that I specified, the K points, what things I put in. This is the analysis of the K mesh, so it's figuring out how to get hold of the right finite difference expression for the position operator. That's a bit of analysis. Slightly more here than we'd normally get because I think we've turned the verbosity up slightly. So there's a bit more output than you might typically expect, but why not? And then it really doesn't do very much work. I mean, it took a fraction of a second to do that. But the important file that it's written is ex1 nnkp. Let's just have a look at that. So this tells QE what to do. Okay, it tells it about the real and reciprocal lattice. It tells it all about the K points, so it can check it's consistent. Here it tells it about the projections. So it's basically saying make sure you do project onto these types of orbitals. Okay, it's quite tightly specified file format. If you're interested, it's all in the Wannier90 documentation. And then there's a specification of for each particular K point, we need the overlap with its neighbors. And this is a specification of exactly which K points we need overlaps between. Okay, so that's really for QE to read. So we now need to run PW to Wannier90, so all those overlaps can be computed in the plane wave code. And there is a file 06. Here we go. Let's have a quick look at it. So we've told it here that the optional ones here. So this is ex1, that's the seed name, so it's going to read ex1.nnkp. We've told it to write the A matrix, AMN. We've told it to write the M matrix, MMN. You're going to pretty much always want to do those things. That's what's necessary for the Wannier90 calculation. We've also told it to write the UNK, so that's the block state. So there'll be 64 quite large files with the block states. Now, that is only needed for making pictures. It's not needed for constructing the Wannier functions. They do take a bit of disk on space, so only do that if you are going to plot the Wannier functions. Okay, so now we can run PW to Wannier90. Hopefully I've got everything right here. Let's call this PW to van.out. Again, this has got a little bit of work to do, so it may take a few moments, and I may just cut the video to speed it up. Actually, it finished while I was talking, so right. Oh, lots of files now. All the UNKPs that are relatively big, PW to van.out, and you'll notice before that there's AMN here, MMN, and the IG. Okay, so they're the essential inputs that Wannier90 is going to read. AMN overlaps, projections onto local orbitals. MMN is the overlap between K points at the nearest neighbors, and IG is the list of eigenvalues, and all the UNKs are the block states. So they're all there. Right. So let's run Wannier90. We've got there. So Wannier90, 90.x, no PP this time because we're running it directly, and the seed name, which is Ex1. Doesn't take very long at all. Okay, that's good. And what can we see? Yep, we've got some band structure files, and we've got Ex1 wout. So let's have a look at that. So this is the output file. Again, we saw some of this before. This is, for example, where the atoms are, what the projections are, what the K points are, all the parameters that we've set, including the default ones, some details on the K mesh. It's read the overlaps and the projections with timestamps on those. That's good. And now we entered the vannerization section. So this is our initial step. Okay, you see that the spread is 6 point total spread here. It's there. These are the centers of the Wannier functions, which if we did a bit of crystallography, we would find are bang on the middle of the bonds. To a good numerical approximation, the spread of all of them is the same. The sum of the spreads is 0 in this case. And we've got a decomposition of the spread if we're particularly interested into different so-called diagonal, off diagonal, and but there's the total spread here that we're actually minimizing. I think you will have had earlier theory talks that will have talked about the decomposition of the spread. So that's the initial one, and then we go through a conjugate gradient minimization, and the spread is then minimized. And actually, we've told it to plot out every 10 steps, and you can see by 10 steps. So after the first step, the spread decreases by 0.1 times 10 to the minus 2, but by the 10th step, we're down to 10 to the minus 10 to the minus 13. So we go and do 100 steps because it's pretty quick, and eventually we've effectively reached machine precision. So there isn't very much that's changing. Okay, and eventually we plot out the total spread here, and the so-called invariant spread, the diagonal element of the spread, which interestingly is exactly 0. That's enforced by is a consequence of symmetry. See the original Mazzari-Vanderbilt paper if you want to read more about the theory of that. And then there's a small off-diagonal contribution. Okay, well, that's all good. Having done that, Wannier90 will then take the Hamiltonian that it has and calculate a interpolated band structure. So Wannier interpolation of the eigenvalues is exceptionally quick. It calculated the band structure here in 0.045 seconds. Okay, well, actually, the timings are so small they're almost not reliable. So I'm not quite sure why those two numbers are very slightly different. Their timing. Some of this is just the calls into the subroutine, so it's a fraction of a second. Okay, it's very, very, very quick. All right, well, we could have a look at that band structure. So to do that, let's see if I can do this remotely. So launch new plot, and I will load this file. Okay, not the prettiest band structure in the world. We could tidy it up with a few extra commands, but you get the general idea. We've told it to go from L to gamma to X, and here are our four bands that this one is. There's a degeneracy in there, so we can only see 3 at this point. At the gamma point, we've nicely got the threefold degeneracy here and the single S state down at the bottom. So that's our Wannier interpolated band structure. Well, that's nice. Right. What I'd like to do though is compare that to the QE1. Okay, so let's have a go at that now. There's a few nice commands that we can set with GNUplot to make things a little bit nicer. I'll just pop them across. Oops. Yep. Okay, these are just some settings I need to do, and hopefully this one. Now, I just will note, you have to be a little bit careful if you're cutting and pasting this from the PDF, because depending on your terminal, you might find that the quotes get messed up and give you a kind of weird effect or an error message or something. So just make sure that you've got the quotes around qebands.agr and ex1 band.dat as proper ASCII quotes. If in doubt, delete them and retype them on your keyboard. Okay, so let's just pop that across. Okay, so I am zoomed in here. So obviously what you can see up here, the purple color are the QE bands. Okay. There are many more up there. I could have zoomed out and plotted those. The Wannier ones only cover the lower 4 bands because that's all I've asked for. And you can see, maybe it's just a little easier if I, what we could do is something like this. So if I plot points there, and because there are a lot of points, every 5, why not something like that? So there we go, that's nice. So what we've got is the purplish color are the QE, so that's full SCF accuracy, full plane wave calculation, and the crosses are coming from the Wannier interpolation. So the lower S band extremely good, the upper band is very good. Everything is reproduced at gamma. Well, that's in the original mesh, so we'd expect that to be the case. And we've got a little bit of deviation in the curvature of this band here. It's not bad, but it's not great. Why is that? It's because we constructed our Wannier functions from a 4x4x4 grid. If we went up to 6x6x6 or 8x8x8, this agreement would get better. Okay, certainly probably by 6 you'll have a difficulty noticing it on a diagram. The convergence, as I may have mentioned earlier, is exponentially good. Okay, so that's all nice. Now that's only part of the band structure. So what I could do, let's. Why don't we? So first of all, I could restart the calculation, so I don't need to redo the Wannierization, even though it was incredibly quick, but I can do that. And why don't I extend the range? So let's do a slightly bigger path. Okay, let's pop this in. There we go. And we can rerun Wannier90. There we go, fraction of a second. And if I new plot again and just load there we go. So that's a slightly more extended path. The interpolation is so quick that it takes no time at all, and we've got I might recognise that as a more common band path for silicon. Okay, so unlike the plane wave calculations where each K point is a little bit expensive, almost every K point here is almost for free. It's really quite quick. Okay, so there's no reason not to do a more lengthy, complicated band path if you need it. So the last thing to look at is, let me just quit and clear my screen. Let's have a look at actually looking at the Wannier functions. Let's see what they're like. So for this, I will edit the win file. I'm doing a restart. Okay, I'll not plot any bands because there's no need to, but I'm going to uncomment this. So Wannier plot. So this is going to take the UNK files, so it's going back to a basis set and the unitary transformations that we've got, and it's going to plot the Wannier functions. And the Wannier functions are not periodic in the unit cell, they're periodic in a much larger a supercell that corresponds to the K-point sampling. So I need to plot them in a supercell of the unit cell, so here I'm doing it in a 3x3x3 one. it can be quite expensive to build a Wannier function, so in some cases you might want to just restrict it to certain numbers, but 4 here will be quite quick, so I'll do that. Okay, so hopefully that's enough, and we can just run Wannier90 again. Now this will take a little bit longer because remember it has to go back to the plane wave basis to construct it, but actually, hey, it's done it already. And if I look at what files it's created, there we go. It's created an output file, but also 4 XSF files. You can also put it out in cube format, but XSF is opened by Xkristen or indeed by Vesta. So if I just have a look at ex1.wout, okay, then there's my output file. This is all the stuff that we had before. We did a restart, so it just overwrote, it just appended to the end. And here we go. So this is the calculation that we've just run, restarting Wannier90 from plotting routines, and it's done something useful for us. It's plotted out the real imaginary to real ratio. Okay, so it has a look. The Wannier functions, they're not imposed to be real. Now we're doing a system without spin orbit and magnetization, so we're going to expect that our maximally localized Wannier functions should be real, and that's a sign that we've converged them well. And indeed, what this is telling us is that the imaginary component is always very much smaller than the real components. These are essentially real. We could probably work a little bit harder perhaps and get these numbers a bit smaller, but actually this is pretty good. So these Wannier functions are to all intents and purposes real objects. Okay. So that's good. So I've got my my files now. What I need to do is run Vesta. Okay, so I'm going to run Vesta on my local machine because it's just a little bit quicker. Vesta's a really nice program, very easy to install. So let me just okay, let me open this file. There we go. So I've just browsed, open up the XSF file. And here is a Wannier function that we've just calculated for silicon. Okay, it happily looks exactly like we'd expect it to. Okay, it's centered on the bond in between 2 silicon atoms. Okay, we can play around with the isosurface a little bit. So, for example, it's chosen my isosurface level to be about 4. If I turn that up to 8. Click somewhere else. There we go. It's made it a little bit smaller, higher contour value. The negative parts outside there have kind of gone away. If I take this down to about 2, I get a much bigger Wannier function. Okay, and the sort of negative lobes in these back bonding regions are much more apparent. Just want to highlight one interesting feature. Vesta doesn't necessarily do a particularly good job of it's plotted the crystal structure in this little box and the grid in a slightly bigger box, but we can tessellate the grid. I'm not quite sure how to tessellate the crystal structure. I'm sure there has to be a way. So let's go to boundary. Now what happens if I put in 3 by 3? So I'm going to draw a supercell. What would happen? I get this. Ooh. So the Wannier functions, as I said before, are not, if we constructed them from a infinite sampling, a continuous integral of the Broughon zone rather than a finite mesh of k points, then a single Wannier function would be isolated within the crystal. When we sample it with a finite mesh, however, they are periodic. Okay, so if I went and did a calculation on a 6 by 6 by 6 k-point grid, you would find that these Wannier functions would be further apart. If it was 8 by 8 by 8, this one wouldn't be here, and the nearest neighbor would be this one over here, for example. Okay, so it's just something to bear in mind when you're plotting, particularly if you've got very small k-point grids. Okay, and I think that's everything I wanted to show in this example.